Karen Davis from Stony Brook University for the last talk of the day. She will talk about punctures of COR, critical orbit relation curve.
Hey, thanks for the introduction. Thanks so much for the invitation to speak and come here for so much long in Cambridge. And also just want to say happy birthday to Phil. I don't know where he is, but I just want to say from everyone else, you might have to worry that they just like you for your math, but I don't really do transcendental dynamics, so I like you because you're a cool guy. Yeah, so I wanted to talk about some joint work with Alex and Jan Kiwi about some of these parameter spaces that we're calling core curves that I think are kind of related to these special curves, but it's not really material. Okay, I should have tested this for sure. Oh, no, there. But also a plug. In 2028, we're going to have a semester conference on a lot of these themes. So if you like institutes that have green logos, and then kind of white, green, abstract, then I think this could also be a good conference for you. And also, this photo, and then also the photo I think from this conference were made by Denny Stoll in this program Dynamo that you guys should Google. And there's a lot of really cool fractal exploration you guys can do there. So just a few more plugs. Okay. So here's what we're going to accomplish today. First, I'm going to give you some background. We're going to talk about moduli spaces. We're going to talk about what are these core curves. And we're going to talk about degenerations. And then I'm going to give you the main classification result that says in these hyperbolic core curves, we get 4 types of punctures. And so this is going to be the picture of the day, I guess, this little 4-fold classification. We're going to see this from 3 points of view: dynamical, geometric, and then also combinatorial. And then we're going to give it a good application, and we're going to apply this to counting punctures problem, and we're going to talk about the pure N0 curves in RAT2. All right. Am I speaking too fast? I know my native language is English, and even for Americans, I speak quickly. So please do not hesitate to slow me down. Okay, so part 1. So RAT-D is a collection of all degree D rational maps from the sphere to itself. And then you can consider there are 2D minus 2 critical points for a degree D rational map. So you can consider a 2D minus 2 cover of this space to RAT-D critically marked. And this is where you have your critical points, and then all of your critical points have names. So in this point, C1 and C2 are not necessarily interchangeable. If I want to mark them, this means that I can say that C1 is doing something and C2 is maybe doing something else. Then the classical thing that we're going to look at is this moduli space, and this is when we mod out our rational maps by our automorphisms of our underlying space. In this case, these are just Mobius transformations, and it descends for both the critically marked maps and the unmarked maps. All right, then what I want to say is that a critical orbit relation, this is just an equation that relates the grand orbits of 2 different critical points. So it's saying that if Ci has a common iterate with Cj, that's a critical orbit relation. This is sort of the building block if you're imagining a dynamical portrait where you're prescribing the forward behavior of many different critical points. Critical orbit relations are the things that does that. Then a core curve is then a one-dimensional variety in RAT-D, but we're going to be looking under critically marked because we want to be able to distinguish which critical point is doing something. Just because one of them is in an n cycle and another is in an n cycle, that doesn't mean we can necessarily exchange them. The fact that it's one-dimensional means we have one free critical orbit, and these guys end up being algebraic curves. So if you imagine drawing it, then this maybe is a little algebraic curve. I don't know, this doesn't look smooth, so this probably wasn't a good choice for how to draw it. But then there's some line at infinity that you can imagine where the ends of your curves are, and then when you intersect the line at infinity, you can get some amount of punctures. And to imagine the degenerations in this family is that if you have this curve C, then its boundary is the intersections at infinity, and these are then isolated singularities. One point I just want to make, because when we're talking about some of these classification results, we're talking about how things are degenerating. And I want to say when you're degenerating within a particular core curve, you have particular speeds of approaching that are already happening. So if you're approaching, say, this boundary point upstairs, to approach within the core curve means that you have to approach within the algebraic conditions that are already formulated. I think this is something that Laura mentioned earlier today for why in her method sometimes you don't have to worry about, say, sequences of degenerations from transcendental rates, for instance. Okay. And then it's a theorem of transversality from Adam Epstein, and then also from Levin, Shen, and von Streen, that core curves are smooth. And the upshot of this is that a smooth one-dimensional complex variety is a Riemann surface. So this means that our core curves are finite type Riemann surfaces that are possibly disconnected. But just because the curves themselves are smooth, this does not necessarily mean that the boundary points or the punctures are smooth, because you can have a local model near your puncture that looks like t maps to t to the m. Okay, and if m is bigger than or equal to 2, this isn't a smooth parameterization. You'll have some kind of singularity that has some multiplicity up there. That's something that will be relevant if we're trying to count the number of punctures in our core curves. So this is just to say, this is just like a helpful way that I like to try to imagine a different way of thinking about core curves, is you can imagine as sort of like an intrinsic Riemann surface. Maybe to a lot of the algebrators in the audience, this isn't really like material, but it helps you think about some questions about saying, well, in particular, which Riemann surface is it, and how many different punctures are there? And then if we're trying to imagine degenerate families, we're imagining this disk, punctured disks worth of maps as we're degenerating towards a puncture, and we're asking what information can we preserve into the limit. Okay, and then the last definition I want to give for you is what it means for a core curve to be hyperbolic. And I'm going to say a core curve is hyperbolic, essentially if it's PCF hyperbolic, and then 1. So what this means is if you choose an abstract portrait, the first bifurcation you can imagine is whether or not there exists one disjoint-free orbit, or if there doesn't. So for instance, over here, there exists one free guy that's disjoint from the portrait upstairs, but for instance, in these merge type varieties upstairs, there's just like one graph worth of it. Okay? And then if there is one disjoint-free orbit, it'll be hyperbolic if every critical point sees another critical point in its forward orbit, and it'll be subhyperbolic if it doesn't. So this map is subhyperbolic, it's not hyperbolic because this critical point maps into a repelling cycle. But for all of these examples up here, these are different examples where every critical point that's in the sort of not free cluster sees a critical point in its forward orbit. So we'll see this example up here is the markings for our quadratic polynomials. These ones are irrational maps that have a critical point in a 3 cycle, and then one is free. These are our pure n curves in Ret 2. This is a fun example that we'll talk about in just a bit of cubic rational maps that have a cubic point mapped to a simple critical point mapped to a regular point maps back, and then a free cubic point. Oh, that's too many. This should be a 2. So there's a whole bunch of different combinatorics that you can study that if you get bored with like dimension 0 PCF combinatorics, you can try to think about higher dimensional portraits. And then also here's another example for different polynomials. But of course, when we're ever studying algebraic variety, or these core curves, they also come equipped with some bifurcation locus inside. And I think this is like why these become the dynamically natural space to sort of do complex dynamics in, is because the place we all started, well, some of us, I guess, was in the Mandelbrot set. And then these, the Mandelbrot set is not the same as the variety that contains it, it's the bifurcation locus inside of it. So these are these examples of core curves have many interesting dynamics with many post-critical finite completions of the free critical orbits. So these are some of the different pictures of the corresponding portraits that we had on the previous slide. All of these happen to be connected, but in general, they don't necessarily need to be. But the other thing you'll notice once you start studying some of these higher degree curves, when you look in the Mandelbrot set, it's kind of not apparent. You never really come to terms with the puncture, I guess. Like sometimes you work in the shift locus or the escape component outside, but you're never like really directly working with the puncture. It doesn't really come to mind. Once you start working with pure n curves or some of these higher degree examples, you very quickly come to understand that your punctures are really a part of the space and they require some analysis. And I think a lot of people have studied these things pretty comprehensively in a lot of ways, including Laura, who's here, and then, let's see, I'm going to try to guess who everyone else who might be here, but I think a lot of people have worked on a lot of things about punctures that I'll also try to mention in just a little bit. But I also want to talk about what are we thinking about when we're talking about degeneration. So when we are degenerating, we're taking this punctured disk around a puncture, And while t goes to 0, this introduces some action on a Berkovich space. I'm only saying this here if you were here for this last week while Charles was giving this really brilliant mini course so we could help understand concretely what this meant. But this is a bit of a complicated way for me personally to understand that I guess I want to say is that at least in these core curves, you kind of don't have to think about in terms of that, but definitely on a larger generality, it's definitely important. So the point is that when you're degenerating to the limit, there exists some kind of thing that completes it that you can think about as like an infinite tree of spheres or some infinite kind of R tree. And where these different bubbles are coming from in this sort of tree of spheres is, well, we have to, if certain points are colliding together to correspond to a degeneration, then we want to blow up those points into a new sphere to pick up on the differences of speed at which those 2 points are colliding together. So for instance, in this example right here, we might have 5 marked points. These 3 are kind of doing their own thing. And then these 2 yellow points are colliding together at a rate faster than these other ones. From these 3 point of views, these points become the same point in the limit. But when we blow up these 2 different points, now they live in their own sphere, though you can distinguish them only into when you're looking into a tree of spheres. So, but still from these 3 spheres point of view, they just see the node that came from this sphere. So we're not actually changing anything, it's just a more complete description, and this is kind of what the Berkovich space is encoding. So I guess some of the questions are, what are our limit objects? Are they ever finite? And how do they compare to other trees of spheres? And then also, you don't want to just think about the abstract curve, you also want to think about how does the bifurcation locus live inside in a local neighborhood around your puncture. And then you want to use this to be able to maybe count the number of punctures that you have in your curve. So how does convergence make sense? Well, if F is just a normal PCF map, the thing we do in order to study its dynamics is that we take the set X of marked points, we look at its pre-image under F, and then we look at an inclusion to identify the domain and range in order to do dynamics as a cover and then an inclusion. And this works when our 2 maps are the same points, but when we're degenerating our families, if we have lots of marked points that are colliding together, then while we do this pre-image step, we might have more points that are getting closer together, so we had to do a different blow up, and we might have a different space upstairs when we want to consider our cover. So to get around this, then we need to really consider these triples of maps. If these get too confusing, I'll tell you where you don't have to think about them, at least in terms of the classification. But basically what's happening is that if we're considering a core curve, and let's just say it's a hyperbolic core curve, so we have this sort of hyperbolic marked set that I'm saying is sort of in pink, that this X naught set, and you might have to take a few more pre-images of it, but let's not worry about that. And then you'll have this pre-critical point. Then we can represent the total post-composition, the forward orbit of all of our critical points, as this finite set X naught union just the image of our free critical value. So if this free critical point maps, say, to V1, maps to V2, etc. Okay? So then we're going to define that that's our X naught to be our finite marked hyperbolic set. And then Xn is going to be just adding to that set n images of the free post-critical value. So we haven't taken any pre-images of the marked set yet, but then we're going to in this Xn tilde set where we take a pre-image of X of n. And what lets us do is like actually isolate the properties of the cover and just coherently make sense of domain and range. So don't worry about this too much if this seems a little too confusing still. The point is that once we've abstracted our cover, once we take many different pre-images, these sets move holomorphically in T. Yeah, I actually don't know if I can go back. Yes, I can go back.
No, but say that the forward iteration of the critical value belongs to which set? To X naught or to the other one?
No, it doesn't belong to X naught. So X naught consists.
Yeah, because this union is not just X naught and union 1 point, right?
Yeah, so it's union of just 1 point, the critical value.
Or what about the next iterate?
That'll be in X1.
So you're not taking all of the post-critical of this frequency?
Exactly, we're sort of doing it a step at a time.
That's not what was written there, at least. But, okay, sorry.
Oh yeah, sorry. Then in that case, yeah, sorry. Then you're right. This should be the union over all of the guys. We're just looking at partitioning it into the gradation by taking different ends. Thanks for that. The point is then we can look at convergence here, where under these dynamics, these triples converge while t goes to 0. So if we start pinching off certain points and some points are starting to get closer together, this is just recorded on this cover information, and then this cover information is then something that converges in the limit. Okay, so then that's
what was T of T0s? Is that the component?
sorry, TOS means tree of spheres. Because we're converging some tree of spheres here is like just a concatenation of two different spheres, a limit right now. And just, I guess, maybe to continue this example, minus 15 minutes or something? Oh, I have 15, okay, sorry. So this example, for, okay. Okay, so let me just move on just for the sake of time. In terms of the sort of main theorem that came from this work with Alex and Jan, is that if we're looking inside of a hyperbolic core curve, all punctures admit some admissible cover f that acts on this finite tree of spheres, so that when we look at f of t as converging to this action on f on this tree of spheres, the free critical orbit accumulates on a unique node in that tree of spheres. What allows us then, in order to give a classification of these punctures, is based on how fast the free critical orbit is accumulating on this node of our tree of spheres. And there's 4 different speeds, I guess, of convergence that you can consider. The first kind is parabolic, in which z is converging towards the node as like z goes to z plus 1, 2, 3, 4, 5. So it goes that quickly. For attracting, now it goes by a power of lambda. By super attracting, it'll go by a power of degree d. And then by collapsing, it's sort of a constant map that maps exactly onto the node. And this was recorded, and this is kind of why we needed the triple formalism, is because this is when our pre-image trees of spheres change the domain in range, when a whole sphere collapses onto a point. So this is the dynamical classification. And the point is that each one of these then also then has a geometric interpretation. That the action of f, and in particular, the behavior and the quality of its non-PCF rescaling limit, if it exists, determines the nearby geometry of the bifurcation locus near our puncture in our curve. So in particular, the sort of mapping on statements for this is that in these parabolic cases, we recovered that our puncture is on the boundary of a hyperbolic component via a cusp. This was some work that we did a few years ago with Xavier Bouffe, that Alex and myself and Xavier Bouffe did to generalize the theory of parabolic implosion to apply here, that I'll just mention in just 1 second. Then our other case about these attracting punctures, that if you're going to the puncture sort of multiplicatively fast, then this means that you're somewhere in the bifurcation locus for sure. All of the examples that we know are on the boundary of a hyperbolic component. In general, it's not too hard to cook up an example of an attracting puncture that's deep in the bifurcation locus, but we can't necessarily find them for hyperbolic core curves, maybe. Maybe they exist. I mean, I don't know. Then if you're going to the puncture like a power fast, like z to the d fast, then that means that you're subsumed and you can construct nested circles that are converging to your puncture, which means that you're not, in particular, you're not on the boundary of a hyperbolic component, your puncture, that you're somehow buried in the bifurcation locus. And then this last case about this collapsing case, that if you're shrunk, like if you have a whole sphere that's mapping like a constant map to your node, then this means that we are we're a virtual center of a hyperbolic component in this last case. Okay. So to just give a few quick examples of some of these different types, the parabolic maps, these have different fixed points that are colliding together. This is an example in Pier 3.0 that has multiplicity 1, which tells us that we're on the boundary. The multiplicity here means that we're on the boundary of 2m many different hyperbolic components. So the fact that this guy has multiplicity 1 means that we're on the boundary of 2 different hyperbolic components inside of Pier 3. And in particular, this statement that I mentioned about the rescaling limit tells you asymptotic geometry information. This is in particular if you look at one of your small spheres that contains the critical value, this is the special node that I was talking about, then it converges towards a parabolic map on the boundary of this node, like the map z squared plus 1/4, which is the map that has the cauliflower dynamics. So locally nearby in the parameter space, you'll see the same structures that are just determined by the Lavor's map of that parabolic map. But more general phenomena can happen, and this is just like one example for this particular dynamics. Let me just keep going, I guess, for the interest of time. The other example about attracting dynamics, this is a cubic core curve that has 3 simple fixed points, and then you have 1 free critical point. Some people may recognize this as an example that came from Newton dynamics. And in this example, what happens is that you'll have 2 spheres, and the multiplier on one side of your sphere, on the C of W sphere, is attracting. It has a multiplier, I think in this example, 1/2. And on the other side, it has repelling dynamics with multiplier 2. And the point on the repelling side actually lives in the Julia set of the rescaled map within this sort of repelling small sphere. So we can generalize the notion of implosion to determine that the nearby in parameter space, you have to be, the bifurcation locus, asymptotically when you zoom in, looks like the Julia set in this repelling sphere, which in this case, this is conjugate to just the monomial z squared. So this is explaining why in this parameter space over here, when we zoom in towards the puncture, it looks just like z squared. And in this case, the multiplicity as we compute it is equal to 2. So it's on the boundary of 2 different components. Let me sort of skip on from that, just in the interest of time. In the super attracting case, what it means that our node is actually like the center of a super attracting basin for the rescaled map. For this example that came from this core curve, which was, this should be at least recognizable to Mitsu and probably Arnaud and some other people who have studied non-Levy cycle examples. This is an example where you have the node that all of your free critical orbit of this small sphere are attracting to the node like a power map of the monomial u to the 4th, just using the local coordinate u here. Right, and I really don't have time to talk about this, but using this we can extract a sequence of circles that are approaching nearby that you can kind of see in this parameter space. You can see lots of different hyperbolic components that are arranged along circles that are converging towards our puncture. All right, and then in the collapsing case, this is kind of like the exterior of the Mandelbrot set, that if you look at it from this kind of forbidden point of view, and in this case, the puncture is the center of a hyperbolic component, and this doesn't just happen for polynomials, like quadratic polynomials, this happens for curves of any polynomials, but this is also what you see when you look at hyperbolic components of rational maps that are disconnected. They'll have some kind of stretching deformation that will instantiate this kind of collapse. Sorry, going by very quickly, but the multiplicity notion here, in this case, the multiplicity is just 1, but for higher hyperbolic components, you'll have more Butcher coordinates that are ramified together at the virtual center, so you can understand the multiplicity here geometrically by the number of different coordinates that are there. So I guess to recap this kind of classification, we had a finite triosphere that had a special node, and then we classified the dynamics about how fast the free critical orbit was converging to the special node inside of this triospheres. And there were 4 different types, and each of them mapped onto a different possibility for what's happening nearby in the bifurcation locus. And there's some notion of multiplicity that agrees for both of them. Just very briefly, I want to mention this other kind of combinatorial interpretation for what's going on, is that when we are collapsing to a finite tree of spheres, essentially we're getting some finite multicurve that's invariant, that when we quotient it, we get some small return dynamics. This is just a description of a Thurston obstruction. At least in these 3 finite cases, there's a precise kind of Thurston obstruction that corresponds to the degenerations that you'll get in the boundary. And in this last collapse case, it's more or less the same thing, but it's a little bit more complicated just based on the fact that you're working with these triples instead of like an honest, stabilized triple that stabilizes into just a normal virtual endomorphism. So it's just an example about what you can look at it. Then if you have some Thurston obstruction and you quotient it, you'll get some tree, and there's an eigenvalue 1 obstruction towards all of our obstructions here. And the eigenvector, according to this eigenvalue 1, has different integer entries, once we normalize them to all be integers. And in this case, we were considering one special node this whole time, the one that contained the orbit of our free critical value. So the entry that corresponds to that component of our multicurve will have some integer entry, and this we'll call the kind of combinatorial multiplicity that's associated to our puncture. And the point is that this exactly is the same multiplicity for the geometric sense. So for instance, if this is 2 that we're seeing right here, we're going to see 2 times 2 equals 4, many different hyperbolic components that are around a particular puncture in pure n. And I know I'm 20 seconds over, but I'm going to take 40 more seconds, and then I'm just going to very quickly just say my last 2 slides. But essentially, the application of this is that because we know that the geometric multiplicities agrees with this kind of combinatorial multiplicity that is easy to compute, then we can actually effectively compute the number of punctures that exist in pure n. So in particular, there's a lot of facts that people know about pure n that are secretly all the same fact after this sort of 3 different frameworks. And then essentially, we get some algorithm to be able to start with the polynomials that we have in pure n, and we know that every puncture is on the boundary. But insofar as there are many polynomials that share the same puncture, we can predict this from just the information its Thurston matrix. So then by subtracting the sort of overcount that we got by just counting the polynomials based on the weight of how many are sharing at the same puncture, then just summing it all up, we'll just get directly the number of punctures. And we did this, and this is all up to n equals 20, which is the pure n that is the largest known to be connected right now. And in particular, Jan Kiwi also computed the Euler characteristic. So from just doing the number of punctures, now we know the actual genus. So we've actually pinned down which exact Riemann surface it is. But of course, maybe just staring, once we made all this data, maybe this isn't exactly what you want, a bunch of numbers. So it's kind of a partial answer to the number of punctures or some amount of, because each of these also came equipped with some amount of canonical puncture model information. So I don't know. Okay, I'll end there.
Other questions? Comments?
Does your work say something about the connectedness, or are you just using it as a black box?
Well, so yeah, so the Euler characteristic of pure n is computed assuming connectivity of pure n. So the number of punctures in the genus is all after you know that pure n is connected. So I'm understanding there's, I think, 2 maybe routes for showing pure n is connected. One, I think I've talked about a bit before, and this other way that René Ramadas showed is that if you show the Gleason polynomial is irreducible over Q, this implies that pure n is irreducible over C. And then some Oklahoma State researchers, Doyle, Philly, and Tobin, proved by a lot of magma computations that pure n was irreducible up to n equals 20. So we know that pure n is connected up to n equals 20. So all of this is like legit data. These just like are the surfaces.
But if you didn't know Rohini's work, can you get some?
Well, the one that I could show up to hand is like n equals 5 or something.
But you get the Euler characteristics.
You get the Euler characteristics no matter what?
Yeah. Yeah.
So what is the expected growth then of the genus as a function of smoke?
Okay, so there's something I can write down, but I don't have it in front of me. Let me just tell you after, okay?
Okay, sure.
But it's interesting that maybe what you're remarking is that the genus is growing much faster than the number of punctures. Maybe this was expected to you, but there's some formula. So this is the formula, I guess, is that this is equal to 2 minus 2g, and then you can count then the number of punctures, the number of bitransitives, and the degree of your curve, which is the number of polynomials. And this will just pop out what g is, and then there's a formula for how fast this grows. We don't really have closed form or asymptotics for the number of punctures, but maybe this is approximating what you're asking. I don't know.
I think there was a question.
Yeah.
So of course you have not just a topological surface, you have a Riemann surface. So
Yes.
There's some geometry on it. Is there anything you can say about?
Well, there's one thing I can say.
Curve get shorter, and also would it tell you anything interesting?
I mean, I think this is a great question. I would love to know which particular Riemann surface it is. The only interesting thing I know here is that pier 4 is conformally a throw pillow. Like it's actually, the 4 points are coming from the Weierstrass projection. But for any of the other pier ends, I don't really know how to determine what the actual geometry is. I think some of Jan's work with Araceli and maybe Milner proved an analogous canonical differential construction for poly 3 pier n to show what the conformal structure was. I'm not sure if that works for pier n or not. Jan has been optimistic, I think, but then I think I remember Araceli being maybe not. So that would be what my suggestion of that would be, but I think I really should stop speaking now.
Oh, okay. Since there is a welcome reception now, I think we can keep questions for that, and thank you again.